Human brain did not evolve to handle complex systems. That is why it is so challenging. And by complex systems, I mean the kind of systems which include a lot of internal logical interlinked relations with fine-grained details. So the kind of systems that you can find in modern huge codebases, in large microelectronics projects, even in large modern industrial systems, physics frameworks, mathematics frameworks. So the systems are complex not simply because there is a lot of things going on and there is many fine details, but they are complex because all of these details are interrelated in a very meaningful way. This kind of complexity isn't natural for the human brain to process, which is why it presents a certain challenge to people. The skill of dealing with complex systems comes in whenever you need to solve any particular specific task related to this kind of complex systems. For instance, it first comes in when you need to learn the system to make sense of it, to make the first impression. Then you will need to make some sort of mental model of the system. You will need it to navigate the system, to find any particular thing in it, to understand what it's doing, to find specific spots. If you're a security researcher like myself, then you need the skill in order to identify and prioritize attack vectors in a system, as well as to identify specific attack surfaces inside the system. The skill that I'm talking about is becoming increasingly important, and I'm really not seeing this fact highlighted enough in the public discourse. So we all know that technology gets more complex and it's accelerating. If you are working in any sort of software, advanced software engineering, hardware, like microelectronics engineering, then you face this kind of complexity every day in your daily job. But also currently, the kind of technological systems which are currently at the margins of the technological development, at frontiers of technological development, are presenting this challenge at an entirely new level, like artificial intelligence research, machine learning on one hand, and blockchain technology on the other hand. These both technologies are currently leading the front edges of the technological development at large in our society. And in these specific industries, this problem of complexity is exemplified to the maximum. And in these systems, we already start seeing the limits of human brain capacity with regard to dealing with complex systems in a meaningful way. The skill that I show in this video is universal. I want to make it very clear. It doesn't matter whether you apply it to a code base or to a hardware design or to an industrial machine design or to a physics framework. It doesn't matter. It is a universal skill, or better say, compound of skills, which as I identified it to myself, it's not just one skill. There's many different skills. All of them are universal and applicable to different practical situations. So the skill is universal, and in today's video, I'm going to use this board to demonstrate the skill. Now, I want to say that this is not a complex system from the hardware design perspective. It's actually quite simple. But hardware design like this, hardware microelectronics, is quite good to demonstrate the skill because it showcases a particular aspect that you have to deal with, which I will discuss later. In my personal experience, I work with complex systems every day. This is part of my main job as an advanced hacker focused on binary exploit development and 0 days. Complexity is at the heart of what I do. And this complexity is getting large scale, is getting unmanageable, is getting really huge in the kind of systems that I deal with, like browsers, hypervisors, and kernels. If you ever looked at the code base of any modern software project which is popular, like Chromium codebase, for instance, you can understand what I'm talking about. It's unmanageable. Working with complex systems somehow comes very natural to me. It's so natural that I'm barely aware that there is a certain challenge to it. In fact, I wasn't aware that there is a challenge in dealing with complex systems until a certain point. in my life, because for me it comes very naturally, and this is something that I did starting early in my life, and it's even more like necessity for my particular brain to work with the complexity and to increase the level of complexity. Aside from that, from starting early, from taking it as a kind of my natural skill and working with it in my daily job, I also keep the skill sharp. And you know that in order to keep any skill sharp, you don't just keep practicing it. You have to give this skill more fine-grained challenges. So in order to keep the skill of being able to solve complex systems sharp, you have to give yourself new grades of complex systems. And for that purpose, it's not enough to simply switch to a different type of the system that you're already familiar with. For instance, you were developing for Chromium browser and then you switch to a Mozilla browser. That isn't the kind of switch which introduces enough challenge to keep the skill sharp. Rather, you have to introduce a completely new system, like shifting from software engineering to hardware engineering, or from software analysis to hardware analysis, for instance. Personally, I recently enrolled in a university on a physics degree to study theoretical physics, and currently I'm studying the quantum mechanics module, which I was hoping that it would give me the kind of new level of complexity to deal with, to sharpen the skill, and also to entertain my brain. In this video, I'm going to show you the skill which I isolated from my personal experience, and I'm trying to transfer it in this video to a broader audience. Because this skill of working with complex systems comes very natural to me, I wasn't really conscious that it presents a challenge to many people until I started teaching trainings to professional security researchers, to my colleagues. I have a professional training system which is very niche, very ultra specialized, so I'm not advertising it on this channel. There's completely different audience. In this system, I'm transferring my professional ultra specialized knowledge to my colleagues. And at some point, I started noticing an interesting tendency. Advanced security researchers were coming back to me with variations of one specific question. They were asking things like, how do you actually learn a complex system? Like, you open a code base of Chromium browser. What do you do to make sense of it for the first time, if you see it for the first time? Then how do you identify attack vectors in it? How do you prioritize attack vectors in it? How do you identify a specific spot where to look for vulnerabilities? How do you limit your time or manage your efforts in order to not get lost in the system? So they were asking this kind of seemingly different question, but the essence of this question is the same. They were asking about how to deal with complexity. Now this really triggered my curiosity because advanced security researchers have the skill developed for themselves, 100%. If you don't have the skill, you cannot solve the challenges which exist in this particular field where I'm working. So anybody who works here more or less successfully did develop the skill for themselves. Regardless of that, they are still open to incorporate experience from another security researcher. This was very interesting, so I started looking deeper at what is going on here. Quite quickly I realized that human brain didn't evolve to handle this kind of complexity. If you think about how Homo sapiens evolved, they were hunters and gatherers, and then societies appeared more or less not really so long ago compared to the history of human development. Societies appeared, and with it appeared politics, medicine, sciences, all the kind of systems that can be considered more or less complex. But in fact, those systems, even though they appeared, for one, they were practiced only by very few people, and then for two, they were still not really that complex. If you think, for instance, the moment when mathematics and physics really got complex. For mathematics, that was a bit earlier, maybe around 16th century. For physics, that was definitely around 19th and 20th century. And before that, it was more or less manageable. Which means that the human DNA could not possibly internalize the skill of dealing with complex systems based on this small amount of practitioners and based on the relatively simple systems that they were dealing with. It means that as a majority, considering the statistical perspective on the humans, most of us would not probably have the skill embedded in their DNA. Once I realized that, it made sense, and the challenge is definitely here. Because I have a lot of experience with it, and because it's kind of natural to me to work with complex systems. So I started to looking back at my own processes, and with the purpose of isolating that skill and making it transferable to other people. So when I started reverse engineering the skill based on my own experience, I started noticing how it works for me. And if you wonder how it works for me, when I'm presented with a complex system of absolutely unknown origin, absolutely unfamiliar to me, the first thing which I noticed a bit different from most other people is that I do not have this kind of intimidation factor before that system. Rather, I have curiosity. I have an instant curiosity, and my mind kind of gravitates towards exploring the system. When I actually start working with a complex system, making sense of it, interlinking the relations within it, connecting the dots, I feel a little bit of increased cognitive pressure, which is within the normal bounds. And then I also feel a little bit of that my brain is operating at a certain increased capacity level or increased intensity. But the main thing which dominates all that is that I feel normal. I feel like more normal than when I deal with any social situations, with doing some business, writing some text, anything. And from there, I started actually reverse engineering the processes. What exactly do I do in order to solve the tasks related to complex systems efficiently? I have isolated a multitude of skills that can be absolutely universal regardless of where you applied it. And I have been teaching the skills to my students of my trainings for a few years. I think it works pretty well. I was able to observe the common mistakes that are very, very, very common that people do when they take in the skill, they try to learn it, and they all do the same kind of mistakes. To summarize it, when I started reverse engineering the skill based on my own experience, what I feel and what I do, I realized that my brain basically thrives on complexity. But at the same time, I'm also very conscious of the fact that it is simplicity which solves problems. If you take any problem, any solution, you look deep into it, in the end it will be simple. The skill that I'm going to show you is universal. It can be applied equally to any sort of complex systems, be it hardware design, schematics, any sort of industrial system analysis, huge code base, physics frameworks, arbitrary data set. As long as it is structured as a complex system, you can apply the skill. Another important aspect which I want to highlight is that I wanted to isolate the skill in such a way that it builds only on general cognitive abilities. It does not require any prerequisites in terms of specialized knowledge in technology or any specialized background skills. The skill builds entirely on universal skills of human cognition, like analysis, synthesis, putting things together, connecting the dots, making hypotheses and testing them, and so on. It is very universal. For this demonstration, I'm going to use this little board. It's Orange Pi, a Chinese alternative to Raspberry Pi. I chose it for this demo simply because I wanted something a little bit more esoteric than popular system. And I chose hardware specifically because it has the ability to trigger that kind of intimidation factor that I already mentioned. A quick disclaimer, I do not have any experience with this board as a normal user. I didn't try to build any infrastructure on it. I didn't even look at the original firmware that comes with it. I have no idea. What I did with it is I built my own firmware with a modified configuration of the Linux kernel for my own research processes, and I used it only for my research processes. So if you will get inspired, in case you will get inspired and looking into this, then definitely do your own research on the internet with regard to your specific usage scenario before proceeding to buy it. If you're a hardware specialist, a microelectronics specialist, this looks like a piece of cake to you. But my audience here in this video are normal people. Normal people, when they see computer microelectronics hardware, they get some sort of intimidation response from their brain. And usually they are not consciously aware of that response, neither do they expose it as it is. Rather, this response manifests usually in some sort of rejection with a pseudological explanation behind of it, why they want to stay away from that system, basically, why they don't want to solve any tasks related to it. For example, some people could say, I'm not smart enough, or I'm too lazy for that, it's just not my thing. There are different logical justifications that can be given to, but underlying them is this emotion of the intimidation that a brain of an unprepared person typically experiences when they're faced with a complex system. So the reason of that intimidation is that when you look at this board, you see all of these teeny details, all of these wires interconnected, the microchips, and you know exactly that they have a lot of meaning. Each one of them is very meaningful, very purposeful, and quite powerful in its own right. And you know that all of that complexity, this insanity that looks almost random, it all makes sense, it is all meaningful, but at the same time, you do not know what exactly these teeny things do. And that is the reason why your mind feels intimidated. Apparently, many people perceive complex systems in this way. So this is important because when you start working with a complex system, looking into it, your first task is to bypass this intimidation response. Otherwise, it will block you from exploring it. Your first goal is to recognize it. Being aware of the nature of that emotion is the first step. You know now what it means, that it's just some sort of knee-jerk reaction of a mind which doesn't understand what is this. Once you realize that, the emotion will actually step down a little bit. It should weaken down and you can safely proceed forward to the actual analytical work related to it. So that I would say is step number 0 when dealing with complex systems. Step number 1 would be forming a hypothesis on what it is actually. In many real-life situations, normally this information is a given. If you look at a Linux kernel code base, you know that you're looking at a kernel, and you have certain expectations on what sort of things you can find inside of an OS kernel. What kind of subsystems exist there, elements, relations, potential technologies, and so on. But it is important to realize that this first step isn't granted. And in certain areas, for example, in advanced hacking, which I work in, sooner or later you get presented with systems which you do not know what it is. It isn't a given information to you. It's a black box. And you have to form a hypothesis as to what it is. And forming hypothesis is very important because all the further exploration of the system will be based on it. It is important to be flexible about your hypothesizing and be aware that you're hypothesizing. Because if the initial hypothesis is incorrect and you start doing some work based on it, then it will be meaningless. It will be pointless, it will not give any results. Which is why it is important, as soon as you feel like your further explorations aren't working, then maybe step back and reanalyze, reevaluate the initial hypothesis, and maybe decide that it might be a completely different type of system, and try to analyze it from a different perspective. The next step, once you have the hypothesis, for this, obviously I have a hypothesis that this is a computer board. Even if I didn't know that, I mean, what else can it be? I'd say that the interfaces that I'm seeing here would give it away for me, most of all, and then also the overall structure, how the microchips are located on the board, what kind of elements. Overall, I get an impression that it's a small computer. Once you get hypothesis of what you're looking at, is to step back and look at it from a faraway perspective, to form a big picture of what you're looking at. At this step, it is important to abstract away any small details, just ignore them. Ignore any small details, any wiring, any specific elements. You still don't understand what they are, but it is irrelevant at this point. All you need to do is look at it from the big perspective, remember that it's a computer system or whatever it is, and then you want to create a mental map of what kind of elements you can potentially find in that system. You know, in painting there exists a technique where you outline the large elements of the landscape with big splashes of uniform color first, and then start reiterating to add more details. For instance, a big splash of blue for the blue sky, green for the trees, brown for the person standing. After that, you add, in a fractalized approach, you add a little bit more detailed splash of color on top of that to identify details of the next level, like the splash for the sun, the splash for the tree trunk, and so on. And you keep reiterating that, adding finer and finer details onto the picture until it starts looking like the actual picture. In fact, many watercolor techniques are based on that approach, but what I mean here is that this approach is actually also used in oil painting. There exists this kind of technique, which is closer to what I'm trying to convey here. So our goal here is to outline this big picture of the system with these large splashes of meaning. Because this is a computer board, I expect that on the high level, it will have the CPU and memory. It is the first class of elements that I identify. The next class of elements would be secondary peripherals, so to say, which are technically not super essential, but normally they're required for modern operating systems, like networking adapters, wireless adapters, some storage to store the actual code, and so on. The next splash of meaning or segment of that big picture would be the interfaces, which I would expect to connect this system to other systems. And the next class of elements would be the wirings, because I understand that the elements would be interconnected with each other. And lastly, I reserve a large splash of meaning or a segment in the big picture for the unknown elements that I don't know what it is. I cannot classify it, but I reserve a space for them. Next, we start identifying specific elements of each class and analyzing this board in such a way. So first, I want to find the CPU and memory. I would look into the board and I would guess that the big chip here is probably the CPU, and the smaller one here is probably memory. The largest one should be CPU. Also, they are positioned in the center of the board. It doesn't have to be, but it kind of suggests that it may be the most important thing on the board. And the memory chip here actually has a fine print, which gives it away that it's maybe related to memory. So that might be it. I'm hypothesizing at this point. An important point while we're doing this kind of analysis, do not jump into the internet or to some reference manuals to look up and verify your hypothesis. It is very important because, and it's a common mistake, because if you jump and start researching immediately, then without specialized experience, you will get lost in the details and just get lost in this rabbit holes of information, which is why at this stage it is important to stay focused on this specific high level of abstraction. Do not research. Just remember that you are hypothesizing, you're playing with it, you're trying to understand. It's not solid knowledge yet. So then I identify additional modules which can be related to the functioning of this system. Here, I cannot really identify any sort of peripherals like a networking adapter or wireless immediately. So normally I would read the fine print as well, but here it only mentions some model name. It is not meaningful. So I'm not sure where is some additional peripherals here. I will save it for later. The next stage is that I am filling this segment of interfaces. Interfaces would be expected to find on the periphery because they are supposed to be exposed to connect the board to another computer. So I'm seeing definitely the 3 USB ports, and I also make a remark to myself that it might be that this USB ports implement different versions of USB protocol because they stand alone, and that suggests that they may have a different wiring behind them. It doesn't have to be, but it's kind of an idea. Then there is the network port. I'm not sure how many youngsters are familiar with this port because we're mostly using wireless nowadays. This is HDMI. I'm a normal computer user. It's not hacker's perspective. I know how HDMI looks like, right? USB-C here, which finally the type of USB which finally you don't have to flip around to put it in. This looks like a little switch, it also clicks. This looks like memory card. This can be, generally speaking, either external storage of memory or it can be the main storage on this kind of boards. And then what else? This is the audio jack socket, also getting old because we're mostly using wireless to connect headphones. And that's it. I also can notice this thing and this thing. I kind of can guess that these are also some sort of interfaces, but more like internal interfaces. They don't seem to be exposed to the outer world, rather they are exposed to somebody who is professionally working with that board, who can hook into it directly. And that's it. Next, I look at the segment which, there is a segment which identifies wiring between the elements. Now this part isn't possible to do here because on modern boards actually there are multiple layers of the wafer here which multiplex many layers of wiring inside of them. So it's not possible to see with the bare eye how exactly the wires connect these chips together. And for a normal person, I think I wouldn't even do that step because it's not much informative. Lastly, I have this big section of elements which are reserved for unknown elements. This is interesting because at this point I have classified many elements on this board. I know what it is, but there are also some elements which I don't know what it is. For example, I noticed this little round thing here, and I noticed that there is a little bit of mesh in the center of it, which kind of gives away that this is a microphone. I'm quite confident about it. Then there is this interesting element which looks like a teeny black glossy brick with an oval rounded shaped protrusion on the side. This is very interesting to me, very curious, because I don't know what it is, but I know that this rounded protrusion isn't random. It has specific meaning and purpose for the function of this chip. I also noticed that it does have a little fine print on the top, which I can research later, not now. So I can design it for further research. And similarly, there are other elements which currently I cannot identify. At this stage, I can start verifying my hypothesis and also looking up more details, adding up more details onto my analysis. There is a fine print on many chips on this board, as well as on the board itself, which we can use to look up information on the internet. So for analyzing hardware specifically, the thing that you need, the main thing, is called a datasheet. It's the official technical document from the producer of the microchip or piece of hardware, which gives technical details about various technical details about the specific chip. It does not disclose usually inner workings, how it works, but it does disclose specific technical characteristics, parameters, and interfaces, how you can actually communicate with that chip. So you go to Google and look up something like datasheet PDF, name of the chip, which is printed here, datasheet PDF. For example, let's verify this large chip. The large chip has a print Allwinner H6. So I would go to the internet and look up Allwinner H6 datasheet PDF. PDF part is very important because the documents that you're looking for have to be in the PDF form in absolute majority of cases. And adding this to the Google search very much helps to filter and narrow down your search and find what you're looking for right away. By looking up this way, I'm able to find the datasheet for this H6 chip, which turns out to be indeed the CPU, which is a 4-core CPU here. Similarly, I can look up this shiny silver chip, which has much less details printed on it. It's 859. So I would look up something like 859 datasheet PDF, and the output isn't that good for this search. So in this situation, I would have to be creative and look up something more specific, for example, 859 H6 or something like that, and hope that by adding additional details related to the board, I will be able to find this particular chip. Similarly, I go through all the chips which have prints on it and which I still have not identified, as well as those that I identified and I want to verify my hypothesis. I look up their datasheet specifications to know what it is. As a result of that process, I have a rather detailed mental model of this board, which when you look at the board after that process, it isn't so scary and unfamiliar anymore, because you already know most of the elements here. You would have verified them by looking up the respective details on the internet. So it kind of makes sense on this kind of medium level. Another things that you can look up when researching microchips and microelectronics elements is specification, the word specification, and technical specification, and schematics. But datasheet would be the main one. In many situations, you get lucky and have the name of the board printed on it, so you can literally go to the internet and type the name of the board and find the technical document which explains the entire board in a high-level perspective, but it is not granted. So better learn on the low level how it works. And this thing here, it kind of looks funny, but it must be an antenna, right? Because what else can it be? Once you have a rather detailed, with medium level details, mental map of this system, you can start applying this process in a fractal way, investigating more and more finer details. For instance, in hardware analysis, there exist techniques that allow to take out the outer shell of a specific system on chip or a microchip like this one in order to look into the inner wiring of the chip. We can take a high-resolution picture of it after removing the outer shell and analyze the internal wiring and literally see all the gates, and from there we can even identify, we can even translate it to binary code. But these are already advanced techniques, which obviously are out of scope for this video. My point here is that you can apply this process in a fractal way to derive more and more details about the system. The skill that I just showed you is just one of the many fundamental skills of dealing with complex systems. Particularly, it can be used to quickly make sense of the system and build a concrete mental model or even a concrete diagram of what's inside of it, of its internal structure, architecture, attack surfaces, and things like that. But also there exist other skills, many more universal skills that you need in order to efficiently manage complex systems. I'm gonna mention just one skill, is the skill of finding specific thing inside a complex system. With respect to hardware, occasionally the skill is very practical. In many situations, when we're doing hardware hacking, we need to find the JTAG or UART interface. UART is a serial connector, which can be used to connect the hardware board to your main computer. And UART, or serial line, is a de facto standard to use when debug printing from the operating system. So typically in modern operating systems, you have to enable this function manually. There is a tweak or an option somewhere in the kernel configuration. You say to it that you want to print debug output to the serial port. But on more hackery boards like this one, this kind of function tends to be enabled by default. So you just connect your serial line to the computer and you try to boot the board and it starts printing debug output to the serial line. Now, how do we find it? You apply a pattern. You know the pattern of what you're looking for. UART interface is a 3-pin interface, which is why it is easily identifiable here on the board. This one. There is a standard which defines how it has to be implemented. And by knowing the standard, you know how it should look like on the board. You can find it. Then you would use a specialized type of connector, something like USB TTL. So it's a specialized cable. On one side of the cable you would have a connector for these 3 pins. On the other side there is the USB plug which goes into the computer, and you're done. Normally you try to boot this board, and obviously you would need to launch a client application on the computer which connects to the this serial port and listens onto it, so that when this board starts printing the debug output, you see it on the computer. Another situation where we very commonly need to find something specific on hardware board is the JTAG interface for hardware debugging. JTAG is much more challenging to find. Typically on modern boards it isn't exposed directly, and JTAG itself, it can be several options of how many pins it has, so it isn't so straightforward like a 3-pin UART. In many scenarios on modern boards, JTAG isn't exposed at all explicitly like the UART here. Rather, it would be implicitly exposed through some of the other pins. Like, for example, some of these pins can be internally linked to the JTAG circuitry on the board. And furthermore, on modern systems, very often you have to enable JTAG before you can even use it. So it is kind of already advanced level, but I think the idea is clear here. You need the pattern and you look for the pattern on the system. On hardware it's easy to do because you kind of have the visual perception of it. It can be a little bit more tricky with JTAG. Another common scenario what we want to find on a hardware board is to find the flash storage where it has the bootloader and occasionally other parts of the operating system, maybe the whole operating system. Many embedded devices don't really have a place on the internet where you can download their firmware, and you will need to inspect it. You will need to get hands-on to the firmware in order to find vulnerabilities in it, for instance. And there is no place on the internet where you can download it. So the only way is to find the firmware storage on the board and then dump the code from it to your computer and analyze it from there. This is another example of specific task of where the skill of finding specific thing in a complex system applies in real life scenarios